Hi there, this is about rethinking topological quantum via flux quantization. From the point of view of AI, this could be phrased as the question, can we protect quantum AI from decoherence? So quantum computers are excessively more powerful than classical computers. They are also by using peculiar physics that becomes available at atomic scales. This makes possible dramatic enhancements, in particular for machine learning algorithms, and can lead to a quantum version of AI that would be insanely more powerful than anything that we have today. But this is in principle on paper, because the practical problem is that quantum is immensely noise intolerant. The technical term is decoherence, and it means that existing quantum computers are in fact puny. You may not always hear about this in the news, but in fact quantum computing has a hype problem. The popular hope goes as follows: to live with the noise and just keep fighting it by software. The technical term is quantum error correction. The picture one has is that as a quantum computer runs, a classical computer attached to it continuously keeps measuring it, continuously interferes to correct errors. In fact, you need a classical supercomputer to do nothing but that error correction. So a more profound approach would clearly be to prevent errors from occurring in the first place, already at the hardware level. This idea is called quantum error protection. In fact, there's a tantalizing candidate for this called topological quantum effects. Topology is the technical term for invariance under gentle deformations, and the idea is that information in a topological quantum state is stored much like knots are stored in a rope, where the only way to delete a knot, to destroy a knot, would be actually to destroy the whole system by cutting the rope. On the other hand, the theoretical understanding of these topological quantum systems has remained somewhat superficial. Not all textbooks really admit this, but here's one that does. Also, experimental claims have remained dubious, as you may have heard about just in recent weeks. The underlying reason for this is ultimately that topological quantum is an example of what is called non-perturbative physics. This has been declared one of 7 open millennium problems by the Clay Math Institute, which offers $1 million if you can just solve one aspect of this. Now, at our Center for Quantum and Topological Systems at New York University in Abu Dhabi, we have in recent years run a novel attack on this problem. This comes with a lot of jargon, but the key point is a new approach to the problem of flux quantization. Why is this relevant? Well, because in established experiments they do show these topological quantum states, called fractional quantum Hall or FQH systems. These topological objects, these knots in quantum states, are in fact magnetic flux quanta, the indivisible units of flux. But the state of the art of magnetic flux quantization was almost a century old, going back to this article here by Dirac from 1931, which in fact is incompatible with what is observed in fractional quantum Hall phenomenology. So what gives? Well, we've proven that there are exotic forms of flux quantization that do apply to the nonlinear fluxes that are relevant for these systems, and this finally makes flux quanta talk to the topology in the correct way. This gives a new angle on the physics, explaining from first principles fractional quantum Hall topology. In fact, this is a new rigorous theory that takes the math of algebraic topology via this method of flux quantization to predictions in topological quantum physics. In fact, it predicts new pathways to topological quantum hardware that could open the gate to a new form of error-protected quantum computers, and hence possibly in the far future to a quantum version of general AI. In any case, I just come directly from New York, where with colleagues we were discussing possible laboratory realizations. So please excuse my jet lag, and thanks for your attention.